Good day everyone, and welcome to this fourth lecture in the optimization module. Now today we're going to have a look at differential evolution, which is a really powerful technique when you have to find solutions to problems within a continuous value domain. Now differential evolution is by far one of my favorites, and I think to a large extent because it does its own hyperparameter tuning. But let me show you how that works. Let's get going. Now differential evolution, just like any other EA, is a stochastic population-based search strategy, originally developed by Storn and Price. Now, it shares quite a few similarities with standard EAs, but it differs, and this is that hyperparameter tuning that I was alluded to earlier, in that the distance and the direction information from the current population is used to guide the search. In other words, the extent of the mutation and the direction of the mutation is based on the current individuals in the search space or in the population. It was specifically developed for continuous valued landscapes. Now, if you recall, algorithms such as the genetic algorithm works best with discrete valued problems in that you have a bit string to represent the problem. And in this case, differential evolution uses floating point values, as you'll soon see. Now, for many of the standard EAs, variation and diversity in the population is achieved through two processes, namely crossover and mutation. Crossover tends to give us more explorations, in other words, big jumps within the search space, while mutation allows us to find that local optima, and hopefully the global optima. So small changes is done through mutation, and also mutation is very important for finding areas in the search space that wasn't part of the initialization phase. So that's also a function of mutation. Usually crossover is applied first, and then mutation is applied on the resulting offspring. And mutation step sizes are sampled from some, or usually sampled from some predetermined probability distribution function. So either uniform or Gaussian and so forth. So we know what the mutation extent is going to be. We know the probability of changing a gene might be 1%. We know, for example, it's going to start at 2% and then decrease. We know, for example, it's a Gaussian distribution, zero mean with a specific standard deviation. So that's what's meant by that predetermined probability distribution. Now, DE differs from this approach in two ways. First of all, mutation is applied to a clone of the parent to generate a trial vector. So mutation happens first, and after the mutation is done, only then do we apply this crossover operator to produce one offspring in this case. And then very importantly, and this is where the real power of DE comes forward, is that mutation step sizes are not sampled from any prior known probability distribution function. So let's talk a bit about difference vectors in the role they play within DE. Now, the positions of individuals provide valuable information about the fitness landscape. Now, provided that the individuals are well distributed during the initialization phase, in other words, and also the population should be large enough, the initial population is a very good representation of the entire search space. I mean, it's distributed all over. And the distances between individuals will initially be relatively large. Relative to the search space. So if you pick any two individuals, they would be relatively far apart. But as the search progresses, individuals will start to converge to a local optimum. And of course, you want that to be the global optimum, but the point is they start to converge, which means that the distances between the individuals will start to decrease. And that will, of course, be a very good indication of how big and how large your mutation should be, and also in which direction. And that is what DE tries to exploit. So the distances between individuals are therefore a very good indication of the diversity in the population, and therefore also in which stage of the algorithm we are, whether we're in the beginning, we've just been initialized, or whether you're starting to converge to an ideal solution. And this means that the mutation step sizes should be based on the distances between these individuals. You want large step sizes to explore the search space in the beginning, to find those good areas, and then you want small step sizes to exploit good regions once you started to converge. So once the distances between these individuals have shrunk sufficiently. Now DE measures the distances between random individuals by creating what's known as distance vectors. And these distance vectors are then used to determine the step sizes during the mutation phase. Now let's quickly have a look at some advantages of using this approach. So first of all, information about the fitness landscape is used to guide the search. And what's really great with using distance vectors is that the mutation step sizes will approach a normal or Gaussian distribution if the population is sufficiently large. This means that if you select any two individuals in the population, most of them will have a similar distance between them. It's the tail ends of your Gaussian distribution when you pick two individuals that are very close to one another or very far apart from one another. But most individuals will have a similar distance if you pick them randomly. Furthermore, the mean of the distribution will be 0. And the reason for that is that there's an equal probability of selecting xi minus xj than xj minus xi. I mean, it all just depends on who you pick first, but it's the same probability. So that will give you that 0 mean. A further advantage, of course, of a 0 mean is that you will ensure that your genetic drift is kept as small as possible, which of course is an important characteristic about a good mutation function. Now, what is genetic drift? Now, genetic drift is the change in the relative frequency with which a gene variant occurs in a population due to random sampling and chance. Now, genetic drift may cause gene variants to completely disappear from the population. And of course, this decreases diversity. The effect tends to be greater in smaller populations and smaller in large populations. And specifically within the evolutionary algorithms, if your Gaussian mean is not at 0, it could also favor certain genes to disappear over time. So let's say we start with a jar, and the jar contains 10 red marbles and 10 blue ones. And of course, you also have an empty jar like this. Then you select by random, blindfolded, a marble from the first jar and you inspect its color. If it's a red marble, you take another red marble from a different bag somewhere or another jar and you place it into the second jar of yours. And the original marble that you pulled from the first jar, you replace it, and that's the secret. Then you repeat that process 20 times. So after 20, select the marble, put the corresponding color in the second jar, etc. You'll end up with red marbles and blue marbles in the second jar. And simply by chance and probability, you'll end up with maybe one extra red marble. It might be that you end up with 10 red ones and 10 blue ones again, but you're most probably going to have one extra red one or one extra blue one. And now, of course, you repeat this process. You empty the first jar, and that becomes your new empty jar. And then you repeat that process. And because you had more red jars or red marbles in the second jar, the chances are that you're going to end up with more red ones in this new empty jar of yours. And then, of course, if you repeat this process over and over again, you'll eventually end up with a jar containing only one color. And that is genetic drift. So you deselected the color blue simply by chance. Simply by chance. So by probability, you have deselected the color blue. And that has nothing to do with the color blue. It's simply by random chance. And that is genetic drift. Now, the differential evolution mutation operator produces a trial vector for each individual in the current population. And this is done by mutating a target vector with a weighted differential. That's in short how the mutation works. And then once you've got this trial vector, that is used in a crossover operator to produce the offspring. So let's see how this trial vector gets generated. So for each parent, here we are, xit, we generate the trial vector uit as follows. We select a target vector in some way. We'll get to the ways in which you can choose that. But of course, you can also choose it randomly. But the important part is that your target vector, xi1t, must not be the same as your parent. So I is not the same as I1. Okay, so that's your target vector. Then we select two random individuals, xi2t and xi3t, such that none of them are the same. So I is not equal to I1, I1 is not the same as I2, and I2 is not the same as I3. And very importantly, I2 and I3, this two individuals that you use to calculate the difference vector, needs to be uniformly selected from the population. There must be an absolute equal probability of selecting them. And now we can calculate the trial vector. So we take xi2 and we subtract xi3 from it. So that's that. And this is known as the difference vector. We multiply that with a scaling factor beta, which could be something like 0.5, and of course this is going to heavily influence the amount of exploration and exploitation in the population, but it's some scalar value that you multiply to the difference vector, and then you add this to your target vector. So difference vector multiplied by a scaling factor, added to the target vector, and that gives us our trial vector UIT. And that's the trial vector. Now I quickly want to talk about a problem that might occur with differential evolution when you work with niching or niche areas. Now during the early stages, the algorithm may identify multiple promising areas in the search space, and they might be far removed from one another. So they're very good. Both areas have promising results, but their genetic makeup is vastly different. And because you can select those random vectors from two different clusters, it could happen that you have then very large mutation step sizes due to the distances between these areas. And then you could actually lose one of them because of the large distances and the large mutation sizes, you can actually force good solutions out of a niche area. Now, one technique that could possibly be used in this is to cluster them periodically and then to only use distance vectors from a specific cluster, so that if you've identified good areas, that you can individually optimize those areas and find niche values. And then over time, if one area is fitter than the other, it will get deselected over time. But there's various other techniques as well. But this is a problem with differential evolution, is if there is multiple good solutions spread over the search space, the distance vectors could actually force individuals out of those good areas. Okay, so now that we've got the trial vector, it's time for the crossover. Now in DE, crossover typically takes one of two forms. It uses a discrete recombination of the trial vector UIT and the parent vector XIT to produce a single offspring, XI prime T. So there's the offspring, you've got the trial vector, and of course the parent. Now crossover is implemented as follows. You're either going to, for each allele or each location in the chromosome, you're either going to select from the trial vector or you're going to select from the parent. You select from the trial vector if the component J is in this large set J, capital J, and if it's not in that set, you select from the parent. So it all boils down is which of your indexes is in this set J. And of course, this is known as the perturbation points. And of course, let's have a look at the two common techniques that can be used. So the first technique, of course, is binomial crossover. So here you select a number of random points, all based on the probability PR, and this goes into your set J, and then that is used as your perturbation points. And of course, you have to at least select one, otherwise you're just making a copy of the parent. And of course, the next is exponential crossover. Here you select a random point, and then you select the next few consecutive points, and that becomes your set. So binomial crossover is very similar to uniform crossover, while exponential crossover is similar to two-point crossover. So in Andries Engelbrecht's brilliant book, Computational Intelligence, we see the binomial and exponential crossover techniques as algorithms 13.1 and 13.2. So the binomial crossover works as follows. We start by selecting J star uniformly from 1 to nx, which is the dimensionality of the problem. And then we add that J star to our set J. So we've got that one element in the binomial crossover that's now part of the crossover technique. And then we go through each of the possible perturbation points. So from 1 to nx. Okay, so that's what that does. And then if some random value, uniformly selected from 0 to 1, is smaller than some recombination probability PR, and J is not the same as J star, although this step is not really necessary because J is a set. So if you add something to j and it's already there, it's not going to do anything. But the point is you don't want duplicates. So it's just explicitly mentioned here. So if you've now selected that element, you simply add it. So you take whatever is in j and you add the new index to that j as well. And that's the binomial crossover. And this is very similar to the standard uniform crossover that we've seen with genetic algorithms. Then the exponential crossover, slightly different. We start with an empty set j, so it's empty. And then we select a value j uniformly from 0 to nx minus 1. Now the reason why we work from 0 in this case is we want to have a circular array. And of course then you need 0 as your first index. Then we repeat doing the following. We add element j plus 1. So if we select a j, we select 1 over here. If you selected nx minus 1, you're going to select, you're going to add nx to the perturbation set j. So this adds that first element. It's always going to be added. Then we add 1 to j, whatever it is, and we modulus it with nx. So that gives us that wraparound effect. So if, let's say we've got a 10-dimensional problem, so you'll have index 0, index 1, all the way up to 9. So that's 10 dimensions. So when we get to 9, so let's say j is 9, and now we add 1 to 9, now we get 10. Now, if you can check position 10 in the array, you're going to get one of those lovely array out of bounds or index out of range kind of problems. But now what we do is we modulus that by nx. So we divide by 10, nx is the dimensionality, but we're interested in the remainder. So if we take 10, which is the new value of j now, 10, and we divide that by 10, we're going to get 1. Remainder 0. So that takes us back to 0. So if you add 10, it actually wraps around back to 0. So in this way, you will never get that index out of bounds. You will go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3. You're going to keep on wrapping around in that direction. And we're going to keep on doing this until some random value between 0 and 1, uniformly again, is greater than your recombination probability. Or, in the most extreme case, if your size of your set j is equal to 10. In other words, you've now selected everything to be part of the set j. Then, of course, you also have to stop. But, of course, it's very rare that this is going to happen, but it's always a good thing to make sure that your algorithm is defensively implemented. So this is the binomial and the exponential crossover techniques for differential evolution. Of course, a picture paints 1,000 words. So let's see how a geometrical illustration makes this whole idea a bit clearer. So let's say, for example, we've got this 2-dimensional problem that we're trying to find the best solution for, and it has been indicated here as x star. So over here's the best solution. We need to get there. And at the moment, we've got the parent. So there's the parent, xit, and we've got xi1. Okay, so this is the target vector. So that's the target vector. And of course, then we're going to select 2 random vectors. So xi2, where's xi2? Here it is. So there's xi2, and xi3 is over here. There's xi3. And now, of course, we need to subtract xi3 from xi2. Now, to do that, we take the negative of xi3, so it's just going to be mirrored across the origin. So there's minus x13, and then, of course, we simply add it. So we've got these two, we've got parallel lines if you add it geometrically. So there's the one line, there's the parallel line over here, there's the line, there's its parallel line. So x12 plus negative x13t is over here. And then, of course, we multiply that with that scaling factor beta. Here it is. And here we have beta times x13 minus x12 minus x13. So that's that distance vector multiplied by the scalar value. And of course, that beta value was probably 1.8 or something, because it actually increased the size of the vector, as you can see. And now, of course, we need to add this to the target vector. Here's the target vector. So xi1 plus this value over here that we've calculated in the same way. Parallel line, parallel line. Here's another one. There's the last parallel line. And UIT, here we are. That, of course, is now our trial vector. So for this parent, we've got this trial vector, and now this parent with this trial vector is going to be used in a recombination process to find the offspring. So to do that, to find the child xi prime, so there's the parent, there's the trial vector that we've just calculated, and you'll see that in this case, we've selected the y value from the parent because xi prime is on the same level as the parent, but we've chosen the x value of ui, of the trial vector. So here is the child, the offspring at this location. And of course, if we look at this, and it seems in fact, of course, that the child is actually worse off than the parent. The parent is slightly closer to x star than xi prime because of these contour lines, if we assume that that has some indication of the fitness landscape. So, and then of course, as you'll just see with the algorithm, we're probably going to select the parent to survive, and we're going to deselect the offspring. Okay, so let's have a look at the general differential evolution algorithm. So we start with a generation counter, t equals 0. So that's going to count our generations, and then we initialize the control parameters beta, and of course the recombination probability, that's that PR. Then we create and initialize the population C0 to consist of ns individuals. So we have to select the number of individuals, and the number of individuals is actually quite important because remember, we want genetic drift to be as low as possible, and we have got all those distance vectors and target vectors to select. So you have to select an ample amount of individuals, but we'll get to that. Then while our stopping condition is not met, and of course this could be anything like we've had with standard EAs, so in other words, if there's no progress being made, or after some time has passed, or if you found the best solution or a good enough solution, then you can stop, or just keep on repeating. So in other words, you never stop. You keep on searching for better and better individuals. Then we do the following. So for each individual, for each parent, we just element from the population. T is at the moment 0, so C0. We evaluate the fitness. So we calculate the fitness of this parent. Now we know how fit it is. Then we create the trial vector. So this is the trial vector UIT by applying mutation that we've seen. You pick the two random vectors, calculate the difference vector, multiply it by beta, add it to the target vector. That's the trial vector. Then we create the offspring. Here's the offspring xi prime by applying crossover. We've seen both binomial and exponential, so which is similar to uniform and 2-point, but you do a crossover operation, and then you calculate the fitness of the offspring, and then you select the best. So either the parent, which is the fitness that you've calculated over here, so either that or the fitness of the offspring, the child, and you pick the fittest one of the two to survive. And then we advance to the next generation. So t equals t plus 1. Once you have calculated or created offspring for each individual or each parent in the population. And that's the basic differential evolution algorithm. Now the performance of differential evolution is heavily influenced by a number of parameters. The first, of course, is the population size. Okay. Now, this has a direct influence on the exploration ability of the algorithms. If you have too few, of course, then your difference vectors is not going to be calculated properly. The algorithm is not going to be stable. So empirical studies have shown that your number of individuals in your population must be more or less equal to 10 times the dimensionality of your problem. So if you've got a 10-dimensional problem, you need at least 100 individuals in your population. But of course, it depends on the problem again. But that's the population size. Then the scaling factor beta, that could be anything from greater than 0 upwards. And this controls the amplification of the differential or the difference vectors. xi2 minus x13. Larger values, of course, gives us more exploration. Smaller values gives us more exploitation. Usually constant with beta equals 0.5. But of course, you could also vary it over time. You can start with a high value like 1 and then slowly decrease it to, let's say, 0.2 to actually further help with exploration versus exploitation. Then the recombination probability, PR, as we've seen. This decides how much of the trial vector you use and how much of the parent. High values, of course, leads to more diversity. Low values to more search robustness. It takes a longer time to move from generation to generation, or to change over time. So that's the PR. And that's the three main hyperparameters. And of course, as you can see, there's no mutation factor, because the mutation is automatically determined by the distances between these random individuals that you select from the population. Now, there are various ways in which a differential evolution algorithm can be set up. In other words, you could ask questions regarding which individuals take part in the mutation operator to produce the trial vector. In other words, how do you select the target vector? It could be which individuals take part in the crossover operation with the trial vector. In other words, who is the parent? Which do you select? And who survives? The parent, the offspring? Do you decide immediately? Do you consider the entire population? So there's quite a few variations in how you can select or set up your differential evolution. And because of all these ideas in different ways, there's actually a notation that's been set up specifically to define these various configurations. And this is this DEXYZ notation, where the X, the Y, and the Z refers to specific parts of the algorithm. So if we talk about the X in DEXYZ, the X refers to the method that's used to select the target vector. The Y, the second one, indicates the number of difference vectors used, and the Z is shows us which crossover method has been used. So in the examples that we've seen, in the equations that we've seen in the slides up till now, we've used two techniques. We had DE rand because the target vector is selected randomly. We had one difference vector, and then we had the binomial crossover. But we also had rand1, the same one as this, but exponential crossover. So this is the basic D algorithm that we've just seen. But of course, there's all kinds of variations on this, and that is what I'm going to show you next. So in the first variation, we have DE best 1Z. The Z, of course, could be either binomial or exponential as well. So here, the best individual is selected as your target vector. So the target vector is based on the best individual in the population. So now UI becomes X hat plus, of course, your difference vector. So that's the first variation. Then you have DEX NVZ, and this NV could be any numerical value. So here more than one difference vector is used. The trial vector becomes whatever method you use for your target vector, but now you are summing over your difference vectors. So you would pick random individuals, and every two of them form a difference vector. So here we've got, if NV is 2, for example, you might select 4 different vectors over here. The first 2 becomes a difference vector. The second set also becomes a difference vector, and so forth. Then the next technique is rand to best NVZ. So here we combine the rand and the best strategies to calculate the trial vector as follows. So now you define this value gamma, and of course that's just a constant in your algorithm. It could be something like 0.5. So now we start off with X hat. That's the best vector. This is now for the target vector. Okay, so that's that X hat. You multiply that with your gamma, and then you've got xi1. This is a random vector that is absolutely random. Then of course 1 minus gamma with this random vector that gets added. So this becomes your target vector as the sum of the best individual in the population as well as a random one. And then in this case, because we've got NV here, which again could be 2 or 3, whatever the case may be, we've got a number of difference vectors that's used in this to calculate the trial vector in this way. Then the last one is current to best, which is quite an interesting technique. And then you've got this 1 plus NV. And the reason for this 1 plus NV is, and it's written like this, it could be 1 plus 2 as well, 1 plus 3, is to indicate that we use the difference between the best individual and the parent as part of the difference calculation. So here the parent XIT is mutated using at least 2 difference vectors. One is from the best and the parent, while the rest are randomly selected individuals. So your trial vector now becomes the target vector, however you calculate that, and now this part. So here's the part of the difference vectors calculated from the best individual and the parent itself. So something, in other words, the idea with this is how far is the parent from the best individual. And that should also play a part. And of course, this also helps for that whole idea with the niching as well. And then, of course, here's the remainder, the random difference vectors. And that, of course, gets added. So this is some of the variations that we can get on DE. Now, empirical studies have shown that DE rand 1 bin maintains good diversity, in other words, lots of exploration, while DE current to best 2 bin shows good convergence. In other words, where you start combining the best, for the difference vectors, the best candidate with the current parent. So this gives you more exploitation. Now, since we've got this variation between exploration and exploitation, this immediately should lead you towards a kind of algorithm where you switch. So where you start off with exploration, and the moment you can't, you start to converge, you switch to an exploitation phase. So in other words, that you get the best of both worlds. Guys, and that's it. That's differential evolution. I hope you found this incredibly interesting, as I did the first time I discovered this. It's amazing how powerful DE could be, that it automatically determines what the ideal mutation rate should be. Now, I'm busy with a small little demo application where we train the weights of a neural network based on differential evolution. I'll upload that the moment that is done, but please check that out. I think that will hone in your skills on this whole differential evolution technique. But keep this one on your quiver. It really is an excellent technique, especially for those continued valued problem domains. Anyway, that's it from me. Thank you, everyone. Keep well. See you in the next one.